So, welcome. It is possible to use Audacity to align a top and a subwoofer using their linear broadband impulse responses. Here in this video, I show you the method so-called that I have called Farina Fedele method because it involved my method of the rising point of the IRs that I have showed in the last videos, in the last series of videos on this topic. And it involves also the method of the Professor Farina, Angelo Farina. This is the article that you can find in my blog. On the topic of convolution, so ESS method, exponential sine sweep method, and so for convolution, I have yet written a lot in the last 15 years of articles, notes, and videos. I refer you to this video to understand the topic, okay? For information on the topic of convolution and on the exponential sine sweep method. Here on my YouTube channel, you can find many videos on the topic. Do a search also in the blog with ESS word or convolution. Okay. The interesting thing of this I'm talking today in this video is that we can use a normal waveform editor software like Audacity to align a sound system. Okay, we don't need necessary dual channel FFT analyzer. This is the news. Okay, so I show in practice the method. We involve for this the plugins for Audacity of the Professor Farina Aurora plugins, and precisely we generate an exponential sine sweep with its plugin Aurora Sine Sweep Generator. Okay, we leave the default parameters. 15 seconds the duration of the sweep, the frequency range, etc., etc. So we generate the exponential sine sweep, that is this in the first channel. You can see here the spectrum, okay, and this is the inverse filter reversed in time and re-equalized. I repeat you to the videos, to the articles on the topic. You can see the spectrum that is reversed in time and also equalized to be the inverse filter of the ESS. I'm using the Behringer sound card SEO driver. I record in the channel 1. I'm out from the device from out 1 and out 1 and out 2. And if all work, now I generate the in solo the exponential sine sweep just to see if all work. The system is the classical setup home system that I have used in the last videos, examples, etc. And this is the DSP. We unmute now the top. This is the sub, the sub. We have 20 milliseconds in the top and 15 milliseconds on the sub by default. So as we have learned in the previous video, to align this system, we need 5.4 milliseconds of signal delay in subwoofer plus polarity inversion. Okay. So I check a moment the exponential sine sweep if all work. Don't work. Is muted. Moment. Yes, is mute. Okay, what you have listened now are 15 seconds of ESS, exponential sine sweep. Okay. Now we record this signal test from the top in a new channel. So I record the signal. A little clip here so we can reduce the level and repeat the measurement. Again, a little of distortions here. I reduce again the level. Right? Okay, it's good. Now I record the subwoofer. Mute the top, unmute the subwoofer. New recording. Okay. Now we have the recording of the sweep on the top, and the recording of the sweep on the sub. We need the impulse response, okay, to have to obtain the impulse response of the system with a good signal to noise ratio, with no distortion product on the measurement inside the decay we have measured, okay? So inside the impulse response, we need the process of convolution. So there is a tool, a plugin that a module by Professor Farina that do the convolution for us. I select all the traces and I invoke the Aurora convolver. This is the top. So I write top for clarity. Top, tab, sub, grab. So convolution, Aurora convolver, top as audio data, in the inverse filter as filter for the convolution, and I do the convolution. I leave all the default values. We are at 48 kilohertz of sample rate. We call this top convolved. I do the convolution of the sub recording with the inverse filter again. And now you see here the impulse response, okay? If I do the spectrum, you see the recordings in terms of spectrum. I show you the waveform. If I zoom, now I see the rising point of the subwoofer. I can do a thing. I can normalize this. So I select the trace and do a normalization. Okay, I select this and do a normalization. Okay, this is for me the starting point of the subwoofer. I can zoom a little. I can zoom here a little too. Okay, this is the rising point of the impulse response of the linear broadband impulse response of the top, and this is the starting point, the rising point of the impulse response of the sub. Okay. Now we don't need to be extremely precise. Okay, is sufficient to individuate just the what looks at your eyes as the first movement according to the noise floor. So for me, is good in this way. Okay. So in the last part, in the bottom part of the software window, there is this counter, okay, that you can set as a time or samples. Here we have samples now that are 241 samples, okay? Oh, I want to be more precise. Yes, this is good, probably a little more here. something in the middle of these 2 points. Okay, something like this. Well, I think this we leave 250, for example. Okay, 50. Okay. If I select millisecond, I see 5 milliseconds. The step is here are coarse, okay, are not fine. What are these 5 milliseconds? Plus minus the delay that we need to give to the subwoofer to be aligned with the top, as you have seen before. And so if I select now samples instead of millisecond, I have the number of the sample. So I can be more precise on the calculation of the signal delays I need, because here we have 250 samples at 48 kilohertz of sample rate, a single wavelet, sorry, a single sample at this sample rate is equal to 0.021 millisecond. So we can multiply this for 0.021 millisecond, and we have plus minus the signal delay we need to give to the subwoofer that we yet have find in the previous exercise. Okay. I insert now 5.3 millisecond, so we are at 20.3 millisecond. And now we have aligned the subwoofer to the top. Okay. I can record, for example, the response, the total response of the system now, to check at listening if it works. I unmute also the main, the top, and so I record a new trace of all the system. So I record is exponential sine sweep is in solo. Yes, the first channel is in solo. I record. Okay. Now I convolve the recorded total signal with the inverse filter. So Aurora convolver these to data, these to filters. Continue, calculate. I want to zoom out. Okay, now I delete the recorded trace. Okay, I leave just the convolved traces. I give a normalization to the last waveform. I zoom, and as you can see now, I zoom in the vertical plane. Now the rising point of the total system are aligned. Okay. If I measure only the sub now will be in this position, delayed. Okay. We have lost now the information of polarity, but the systems are aligned in time. If I play both the system, I listen the cancellation. So I just invert polarity for check, and I listen the sum. Okay. Or I can show, I can see this in for what I can. I I I remove the selected option. Where is? I want to return to the recorded. I show you in the article. It's more simple. Okay, so if I do the measurement as I have yet done before, after I have deleted the trace. But if I record the total response of the system, I see that there is a cancellation here in the waveform. Okay, here. And there is a dip also in the frequency response. You select all the channel and perform an analysis to show the spectrum. If I invert instead the polarity, I see the sum here in the waveform, in the recording of the waveform, and also in the spectrum. Okay. As you have seen, I have used a normal, a simple software, free software like Audacity, a simple wave editor to align a sound system. So it is possible. And it is another method in the use of the impulse response linear and broadband. Okay. I hope all is clear. I thank you for watching, and I can stop here all the world. Bye bye. And stop.